In Module 3, we're looking at one chapter, Chapter 3 in Keller's textbook, and addressing minerals and rocks. Minerals are the basic building blocks of solid earth, and for us to be able to have any discussion later on about the comparison of different minerals, it's useful for us to have spent some time addressing both minerals and rocks. When we define a mineral, what we mean is it has to be a naturally occurring substance. It has to be inorganic. That means not made up of carbon. So a tree wouldn't be a mineral. It has to be solid. It has to have a characteristic chemical formula. And there might be some variability in it, but that variability would also have to be defined. And lastly, it needs to have a characteristic crystalline structure. We'll talk about each one of these in a little more detail. Crystalline structure of minerals varies from one mineral to another. When we define crystalline, what we mean is that it's having an orderly or regular repeating geometric pattern of atoms in its composition. And when we look at the various types of crystalline structure, there are a number of families. Some of them are shown here. In the upper left, a cubic structure. In the upper right, a hexagon structure. In the bottom left, an octahedral structure. And lastly, we have a dodecahedral structure on the bottom right. The upper left is typical of halite. You might have seen a large salt crystal that looked roughly cubic in shape. The one on the right, that's a classic quartz crystal that you may have seen at one point or another. The bottom left would be characteristic of a diamond or fluorite, an ore. And the bottom right would be something a little bit more unusual. The dodecahedron might be found in a garnet, which is a gemstone. When we look at a crystalline structure up close, we'll have to look at the relation of different atoms. So here we have rock salt, or table salt, NaCl, sodium chloride, and its unit cell is a basic cube, and we can see that we'd have alternating occurrences of sodium and chloride ions here, and together those would form this cubic structure. One thing that's a little bit inaccurate about this depiction is that the sodium and the chloride ions are not actually the same size. If we look at them more realistically, this is what they look like. So here we have the depiction of the sodium ions that more neatly tuck in between the chloride ions. When we look at how atoms are held together in different minerals, we have to recognize that there are very different kinds of bonds, and we're going to look at 4 of those. We're going to look at covalent bonds, ionic bonds, van der Waals bonds, and metallic bonds. In a covalent bond, atoms share electrons. These tend to create very strong bonds. That leads to more durable materials. An extreme example of this would be a diamond, but even quartz has covalent bonds within it. Ionic bonds, on the other hand, are an attraction between positive and negatively charged ions, and they sit between each other, and there isn't an electron sharing. An example of this, the consequence of this would be that the bond is not as strong, so these minerals tend to be soluble or able to be dissolved by water. They're also more chemically active and more mobile. An example of this would be halite. As you know, if salt is exposed to water, it's going to dissolve. Van der Waals bonds. These are a very weak attraction between chains or sheets of ions, and these are so weak that we'd actually take advantage of them. One example of this would be talc is a mineral, and talc has sheets of minerals that are only very loosely associated with one another, which makes it feel slick to our hands. Another one would be graphite, that used to be used for lead in pencil, and the quality of the graphite sheets being able to rub off easily is what led to us wanting to use graphite centers in our pencils, because it was very useful. So that's how weak they are. You can break them simply by rubbing them across the paper or the talc. We can break those bonds very easily between our fingers. Lastly, we have metallic bonds. This is a very unusual kind of bond, but in this one, a bunch of positively charged ions share a group of electrons. So the electrons are shared by all of the atoms, and this means that electrons can flow from one end to the other end of the sample of the metal relatively easily. This strongly affects their behavior. For metallic minerals, we get a fairly malleable or easily molded materials, and they're also able to conduct an electrical current relatively easily. So aluminum or gold would be examples of minerals that have a metallic bond. When we look at all minerals, all possible minerals, we end up having over 4,000 known minerals, and I don't know them all, but you're not going to have to learn them either. But there are a few that we need to become familiar with, and I'm going to cover those. But when we are given a sample of a mineral, one of the things that a geologist would need to learn how to do is how to use its physical properties to be able to identify what it is. I'm not going to be asking you to do that, but because the physical properties help us understand the behavior of some of the minerals and rocks that are formed by the minerals, it's useful to introduce these physical properties here. Used to identify a mineral is its hardness, and hardness is not really well defined on its own, but we usually define it relative to other substances. So we pick a scale where we have a set of well-known minerals on the left, and we've given each of those a hardness, and they're ranked in order from hardest diamond to softest talc. And you'll see a number of different minerals that you may recognize on the left. We compare that to some features that we use in some objects we use in mineral identification, like a fingernail, a copper penny, a wire nail, a glass plate or knife blade, and lastly a streak plate. And we find that we're not able to scratch a copper penny with our fingernail, but we would be able to scratch a copper penny with a wire nail. Similarly, we'd be able to tell whether a mineral falls between a hardness of 3.5 and 4.5 using a wire nail and a copper penny. So we look to see what can scratch what, and the well-known understanding that a diamond can scratch glass is true. Glass has a hardness of around 5.5, and a diamond, when scratched along a pane of glass, would leave a scratch. But so would corundum, and so would topaz, and so would quartz, and so would orthoclase. And why I mention all that is because even sand grains from the beach, if they aren't well rounded, would be able to scratch glass as well, because sand is composed mostly of quartz, which is also harder than the pane of glass. But we do use hardness as one of the easiest ways or best ways to distinguish between different minerals. We use to help distinguish one mineral from another is fracture. We look at its characteristic fracture type, and some don't really have a characteristic fracture type. Others have a very characteristic fracture type. The quartz shown here on the right two images is a a classic conchoidal fracture, and it's one of the ways that we can identify that we do have quartz. The next property that we use for many minerals, but not all, is cleavage. And cleavage means the characteristic shape or orientation of the particles after you break a large chunk of the mineral up. And here, if you took halite and smashed it up, you'd get classic cubes. If you take calcite and break it up, you'll get these rhomboid type structures shown in this image here. And that's one of the ways that we can identify an unusual mineral like calcite. It's very common, but it's got unusual properties, is by its very distinctive cleavage structure. Let's talk a little bit more about cleavage and depth. We might have one cleavage plane that results in flat sheets or as our shape, and we can see these sheets often pile up on top of one another, creating books of these plates. And an example would be muscovite, shown in the upper right of this table. We might have two cleavage planes at 90 degrees, and that would produce columns of minerals columns in the crystals. And an example would be feldspar, which you can see fairly rectangular cross section to it in the bottom right image. At the bottom of the page, I chose to show an unusual property, and that is that some minerals have an ability to refract light, so that light doesn't move through directly. It's sent off at an angle other than passing directly through. And calcite is a mineral that has this behavior, and the two intersecting lines are shown here as a group of lines once they're transmitted light through calcite, and that comes as a result of the refraction of light. That some minerals have that property, most don't. So it's often very useful and distinctive when we recognize a mineral that does have that property. Luster. Here's an example in the bottom right of metallic luster of galena, and I can tell that it's galena because it has a very prominent metallic luster, but it also has somewhat of a cubic cleavage, so you can see some cubes or some cubic nature to the structure below. The luster in the quartz crystals to the upper right is what you might call glassy, but in fact it's not. It certainly doesn't have a metallic luster. The next property that we'll use is the streak. Some minerals can appear in various forms, and here is hematite with very different luster. You'll see the upper left one has something of a metallic luster. None of the others have quite as metallic a look to them, but notice that regardless of what the shape of the mineral is, it always produces this red, rusty brown streak, and that tells us that that's a hematite sample. Lastly, I'd like to show this image of double refraction. A calcite crystal will take a single ray of light and convert it into two different rays, and we can see both as it's transmitted through calcite, and that's an unusual optical property that's distinctive of a few minerals. Next, we're going to look at the crystal form or the crystal habit. And when large crystals form, they have to form when cooling or evaporation or Other slow processes allow a large number of different atoms of the mineral to accumulate into its classic shape or classic crystal form. In the upper left, you'll see a cubic crystal of halite, which it can form naturally. In the upper right, you'll see the hexagonal crystals of quartz, which only will form if you allow quartz to cool very, very slowly. We use to help identify minerals and rocks is a reaction to acid. A geologist would typically carry around a small bottle of diluted hydrochloric acid, and when you put a drop of this on a limestone or a calcite, you're going to get some fizzing, and that helps us identify what minerals will be in that rock sample or mineral sample. Most minerals do not react with acid, but some do. Some common ones do. Most commonly, it's limestone that we can identify, or calcite that we can identify by its strong reaction to acid. This is very weak. If you ever are in a lab, this hydrochloric acid used for this is very weak. It wouldn't burn right away if you got it on your fingers, but you wouldn't want to wipe your fingers off on your jeans, because you'll end up with a hole in your jeans, because it is strong enough that it will eat through clothing. A few minerals have an unusual property of magnetism. Here we see a magnet holding itself firm against a sample of magnetite. Only iron-bearing minerals exhibit this property typically, and not all of them do. Some have a tendency to exhibit it and some don't. Depends on their crystal structure. Next, we're going to look at rock-forming minerals by group, and we're going to group them by chemistry. And here you'll see the main groups are silicates. Here we have the most common classes are quartz, plagioclase, and pyroxene. Next we have carbonates, and there we have calcite and dolomite, and these form typically as a result of water rich in carbonates evaporating, leaving behind deposits of calcite or dolomite. And notice the chemical composition of calcite, calcium carbonate. This is the one we can always identify by its reaction to acid. It probably shouldn't surprise you that because this can be dissolved by acidic water, the slightly acidic water that we get entering our groundwater systems can easily dissolve this. Water can become slightly acidic simply by passing through even a thin organic layer. So if we have leaf litter on the soil surface, that'll be enough to turn the groundwater percolating through it slightly acidic, which will have the ability to dissolve a limestone. The next group that we have is oxides. These are very useful ores. The very common one that we have is hematite. And hematite is useful because it helps us understand the geology of an area, but it's very common. You can see this in a sandstone. If you ever see a red sandstone, or the classic color of rouge would be present for a rock that has a lot of hematite in it. Also in oxides we have bauxites, which is a hydrous aluminum oxide, which is a major ore of aluminum, and so it's worth noting that bauxite is an oxide. Next category is sulfides. Examples of sulfides would be pyrite, also known as fool's gold, or galena. Each of those can be an ore of the metallic atom that is contained in a sulfide. You also can sometimes recognize a sulfide by the smell of rotten eggs after you crack a sample of this mineral open, or if you don't want to crack the mineral open because you only have a small sample, you might see if the streak plate leaves behind any odor after you take a streak and rub the metal on the little tile of a streak plate. The last category that we have is native elements, and these are fairly rare, but we know them for the special properties that they have when they occur. And some of the native elements that we have are gold and silver and diamond and sulfur. We're going to first look at the class of silicate minerals, and silicates make up 98% of the mineral mass in Earth's crust. Silicates are 45% oxygen and 27% silicon. Silicon and oxygen combine with each other to make up most silicates, and they have a classic structure. Here it is. This is a silicon ion comfortably nested between 4 surrounding oxygen ions. The left-hand version of this image shows the relative position of the center of the ions, but the reality is that there's a greater disparity between the size of the oxygen atom and the size of the silicon atom, and that's depicted in the right-hand side of this image, where you see the tetrahedron is typically much more closely spaced together, or the silicon ion is neatly tucked in the space between 4 adjacent oxygen atoms. The tetrahedron that make up a silicate ways. First, we can have isolated tetrahedron that can make up minerals such as olivine. And if you've ever been to the big island of Hawaii, you might have seen an olivine beach, greenish blackish sand made up of these crystals. Other common shapes are a string of tetrahedrons along a line for a mineral such as pyroxene. You could have a double string of minerals such as for an amphibole. Or you could have many of the tetrahedron joined together for sheety minerals such as muscovite or biotite or talc. Probably the most important silicate mineral is quartz, and you've seen lots of this. In fact, if you've ever gone to a sandy beach where the sand looks clean, then almost all of the sand grains are made up of quartz. This is very, SiO2 is the mineral composition, silicon dioxide, and it's a very abundant mineral in Earth's crust. It's recognized by its hardness and its conchoidal fracture if you have a large enough sample, and it has a wide variety of colors that are defined by impurities within it. Sometimes we even have gemstones made up of quartz that just have a distinct or color that we value, like aquamarine is an example of a gemstone that's made up of quartz that happens to have a distinctive color made up of from those impurities. I mentioned conchoidal fractures characteristic of quartz, and here are 2 different samples. That's if you break a sample made up of quartz, but quartz also has a tendency, when it's allowed to cool slowly, of creating crystals, quartz crystals, and you can see a wide variety of different colors that quartz crystals can have. The next most common silicate is feldspar, and these are a group of rock-forming minerals, and we have 2 main types, alkali feldspars and plagioclase feldspars, and different rocks have different plagioclase composition, and when we go and pick granite for a countertop, it's actually the color that's most characteristic of that countertop is probably going to be determined more by feldspar than by quartz. Quartz is more commonly clearer or cloudy white. The next group of silicates are micas. And micas come in sheets, as I mentioned, and examples would include muscovite and biotite. And here you see a bunch of platy minerals from each of those mineral types. The darker one is biotite, and the bottom three images are muscovite. When we have when we have magma that cools slowly, the minerals that fall out of it come out according to the melting point of that particular mineral. So as something cools, the first things that tend to form are olivine, which has the highest melting point, then pyroxenes, then amphiboles and biotite and feldspar. Then we get to, that is plagioclase feldspar. Then we get down to the substances that cool at the lowest temperatures. So these tend to cool most slowly, bar and quartz. When you look at granite countertop, you're more commonly looking at chemical compositions in this range because they've cooled slowly and they have a more attractive appearance to us. When you look at the collection of minerals on a beach, they're broken up bits of these things on the left because these tend to be relatively resistant to the weathering processes that form a sandy beach. Next, we're going to look at some ferromagnesian silicates. These are the darker minerals in most rocks. If you look at a quartz countertop and see a few blackish areas, they're probably these ferromagnesian silicates. And these are silicon and oxygen in combination with iron and magnesium that form up these silicates. Some examples of these would be olivine, pyroxene, amphibole, biotite, and they tend to weather easier than the other silicates that we've considered so far. They produce relatively weak rocks compared to the other minerals that we've looked at, and some examples of substances that could be built from these would be clays and soluble salts. There's other important rock-forming mineral classes we need to consider, and the first of these is oxides. Oxides form when we have metal atoms combined with oxygen. These constitute many ores that we use for mineral commodities, and these include hematite that we can use to get iron to use for steel, bauxite, which we can use to get aluminum, and oxides of iron aluminum are the most common oxides that we find in Earth's crust. The next category I want to consider is carbonates, and these are very important because we use a lot of them. Calcite is very important environmentally because it has the property of being capable of being dissolved. And so that's going to lead to a number of particular properties that we'll be considering in future modules. So you'll need to remember that calcite can dissolve when exposed to slightly acidic water. So chemical weathering of carbonate-bearing rocks produces caverns and sinkholes and other problems in these carbonates. Another important rock-forming mineral class are sulfides. These would include metal ions combined with sulfur, such as pyrite, and a number of other important ore minerals. These are often associated with environmental degradation when they're exposed to oxygen and water, which will happen commonly in groundwater systems. They can produce sulfuric acid. So when we talk about acid mine drainage, this is one of the most common culprits, are sulfide minerals. We'll get back to this later in the semester. The last class I wanted to mention are not very abundant, but that is native elements. There are some minerals that are composed of a single element. These include gold, silver, copper, diamond, and it's just one single mineral that makes up that one single element that makes up that mineral. But there are a few of those found in the crust in very rare cases. When you look at rock, what we're talking about is an aggregate of one or more mineral. Typically, it's a number of different minerals that are combined together, but there are a few rocks that are composed of entirely a single mineral. Limestone is an example. It's made up almost entirely of calcite. When we talk about ways to classify rock, we're going to probably classify them first according to their mineralogy and how they were formed within the rock cycle. The rock cycle is a worldwide rock recycling system linking the subsurface and surface process together. It's the description of what the processes that form igneous rocks, and that's usually cooling from magma. And so if you weather igneous rocks, they can weather to either sedimentary rocks, or through partial melting can become metamorphic rocks. So it's how one rock type moves to another, and the three main components here are sedimentary rocks, igneous rocks, and metamorphic rocks. Those three rock types are igneous, which is a crystallization of molten rock. So if you start to gradually cool lava, you'll get igneous rock. If you quickly cool lava, you'll get a different type of igneous rock. Sedimentary rocks are an accumulation of layers of sediment from pre-existing rocks. We have a few different kinds of those, and we'll come back to each of these. And lastly, we have metamorphic rocks, which are altered in form and mineral makeup by a combination of heat, pressure, and or fluids. To understand the rock cycle, you really need to put it in the context of plate tectonics, which we learned about in Module 2. The melting of a crustal plate as it moves into Earth's interior will produce magma, which can be extruded up or intruded up into a volcano, such as you see depicted here, and igneous rocks will form. If you subject those rocks to weathering, you'll get sediments accumulating on the coast or in the ocean to form the potential for for sedimentary rocks. If you begin to drag sediments down deep below the Earth's crust, you'll start getting metamorphic rocks. So if you shove two crustal plates together, then you'll get metamorphic rocks formed by pressure. So we have a number of different processes that can work within plate tectonics to form different types of rock. Next, we're going to look at rock laws. Fundamental concept when looking at rock that we need to be aware of. We often use these to try and assess the relative age of different rocks. And it's not that their age really matters that much sometimes. Sometimes it does, but often we like to understand the age of something simply to know what the order of events was that led to the rocks that we're dealing with. So the first law has to do with a cross-cutting relationship. A rock is younger than any rock it cuts. So that if you have a rock, you have to have a rock in place for it to be cut. So the cutting one is the younger one, and the one it cut is the older one. Second law is original horizontality. Now, this isn't a strictly enforced law, but it's the general rule, and that is sedimentary layers are nearly horizontal when they're deposited in most applications. And so we often go in with an assumption that however tilted it looks today, we believe it was deposited in a horizontal position. The third law is superposition. The oldest layers of sediments are on the bottom, and the youngest layers are on the top in a series of layers that have not been overturned. So you get younger and younger sediments accumulating on top of one another. So you get progressively younger as you move up. Next, we'll look a little bit at igneous rocks. Igneous rocks are rocks that have crystallized from molten rock, from magma of some type. And here is an example of what's exposed at the surface now, but which was not at the surface when it formed. It was intruded deep in the earth and only later became exposed as a result of subsequent uplift and weathering. And this is what's left behind. So it's like a frozen version of what must have formed deep in Earth's crust at some point. And here's an example of that type of igneous rock. It's an intrusive igneous rock. What is that? It's on the next slide. Rocks cool slowly and they crystallize well below the surface of the Earth. Individual mineral grains can be seen with the naked eye, typically, in these rocks. These often have inclusions or pieces of the surrounding rock that have been incorporated into the crystallizing magma. So if you have magma that's coming up through a number of different rock layers, it might break off pieces of those rocks and they become inclusions in the intrusive igneous rock that's left behind. If you want to look at very large intrusions, you can get what's known as batholiths, and these are the largest masses of igneous rocks in our crust. In igneous rocks, we might ask, why does magma rise and intrude into other rocks? Once you start to form a magma through melting, the magma is typically hotter and less dense than the surrounding rocks. Because it's hotter, it's relatively easy to shape. It's probably in a liquid form or something closer to a liquid than the rest of the material, so it's more easily moved around. And it's also less dense than the surrounding rocks. Because it's less dense, it's going to have a tendency to want to rise up. With this, by the same process, but in a less, but in a slower process, the way an ice cube would if you put it in a glass of water. So these less dense magma collections move up through the Earth's crust, and then they gradually rise. But that rising will cease when the density differences are equalized. So it only rises up through the crust until it gets to the point where the difference in density is no longer so great that it wants to break through the layers above it. In this case, we're looking at what's left behind after granitic rock has risen up through a limestone. So we had a granite that rose up into a limestone and left behind this pluton or intrusion of granite, and which cooled inside the sedimentary rocks into which this was intruded. In contrast, we have extrusive igneous rocks, and that is, these crystallize at the surface of Earth, and they form as a result of lava flow onto the surface or pyroclastic, that is, bomb-like extrusions from volcanic eruptions. So the bomb-like blast of volcano can produce pyroclast, or even little tiny bits of dust that can travel several states or stay up in the highest atmosphere for weeks at a time before they settle back down. Other examples of igneous rocks would be lava that would emerge in the Hawaiian Islands or in Iceland. These are also extrusive igneous rocks, but of a very different chemical composition. But because they're going to cool quickly, the minerals never have a chance to grow very large, so these end up being very fine grained where you won't be able to see the individual crystals. Here's some examples of some extrusive extruded basalt lavas. So they can form in layers, but because we're on the edge of a volcano, those layers are not horizontal. They're along the they are deposited in the orientation of the slope of the volcano. We're back to this slide again. It's known as Bowen's reaction series, and it helps us look at the chemical composition of different magmas and the associated rocks that would form from them. If you take a magma with this chemical composition, and all these would be mixed because it would be very liquid, well, it would be a very unusual liquid, but it would be liquid. If you extruded it at Earth's surface, it would be a rhyolite, and it would probably come out in a very explosive form. If you intruded it and let it cool slowly, it would become a granite. If you go to the opposite end and have a magma that's formed of these types of minerals, first of all, it's going to be at a much higher temperature than the other batch that we considered. And if you extrude this to Earth's surface, it won't be as explosive, and it will tend to form basalt. And if you let it cool slowly, it would form a gabbro, what's called a gabbro. We don't use very many gabbros in our kitchen countertops. They're not as resistant to different chemicals that we might put on them. In between this high temperature endpoint and this low temperature endpoint, we have moderate or medium categories where dacite and granodiorite would be formed, depending on the process of whether that magma is extruded or intruded into the crust. And another category would be andesite and diorite. If you look at that first rock, first type in that category, that is extrusive rock in this intermediate category, notice that the term andesite comes from the Andes Mountains. The characteristic magma that is extruded in the Andes forms andesite, and because it's the same process that formed Mount St. Helens, it's also andesite that we find there. When we look at igneous rocks in the environment, it's important to understand their properties. Intrusive rocks are generally strong and resistant to weathering. Sometimes when lava flows, it can cool in a particular way to permit columnar jointing and lava tubes, and these impart weaknesses and paths along which water can get into the rock. Careful field study is always necessary before building large structures on any igneous rock. Here is a Devil's Post pile from Southern California that is an example of the columnar basalt. This material cooled relatively quickly, but with enough, but slow enough that it provided an opportunity for these cooling joints to form, and it's classically columnar joints that form in basalt, and these are found in a number of places across the globe, and one of the best examples in the United States is in Southern California at this location called Devil's Post Piles National Monument, I believe. Next, we get to the category of sedimentary rocks. Sedimentary rocks constitute 75% of rocks exposed at Earth's surface. We have two fundamental types of sedimentary rocks. We have detrital or clastic sedimentary rocks that form from broken pieces of pre-existing rocks, and we also have chemically deposited sedimentary rocks or chemical sedimentary rocks. These are deposited when chemical or biochemical processes precipitate out dissolved substances. The most common example of these is of the chemical type is limestone, but rock salt would be another example of a chemical sedimentary rock. Diagenesis is a process, so it's what can happen to sediments if you allow them to become buried and gradually cemented. Diagenesis is the rock forming process, so gradually sediments can be pushed together and cemented or fused by pressure to become sedimentary rocks. Sedimentary processes are, we have a number of different sedimentary processes, and these different processes deliver the sediments to the sedimentary basin. The sediments accumulate as strata or layers. As the basin sinks or the sea level rises, we could end up with several kilometers of sediment, several kilometers thickness of sedimentary rocks that can be deposited one on top of another. The pressure of overlying rocks and the precipitation of minerals within the pores between the grains can cement the rocks together. So all those processes are part of diagenesis, which is a rock forming process. How are the two types of sedimentary rocks classified? Detrital or clastic sedimentary rocks are classified according to their grain size. If the rock is composed predominantly of clays, it's called a shale. If it's composed predominantly of silts, it's called a siltstone. If it's composed predominantly of the next grain size up, sand, then it's called a sandstone. And if it has pieces larger than sand, than pebbles or cobbles, then those would be known as a conglomerate. But we classify chemical sedimentary rocks very differently. We classify these according to their chemical composition, and the most common of these is halite, gypsum, and the most commonly used one is limestone, which is the most abundant of the chemical sedimentary rocks that we find at Earth's surface. That's formed of a single mineral, calcite, calcium carbonate, CaCO3. Environmental concerns associated with sedimentary rocks, we have to recognize that shales, mudstone, and siltstones are often extremely weak and prone to weathering quickly. In a matter of a year or two, you might be able to see weathering occur to some of the most weakly cemented of these rock types. Limestone is generally not well suited for human use and activity because of its weathering characteristics. If you have a limestone beneath your septic field, you are going to be dissolving that limestone more quickly as a result of the installation of your septic field, and that's probably not what you want to do. And it certainly is not what your regulators looking at that topic in your area would want you to do. Another issue in sedimentary rocks is the cementation may be very weak and it can break down. So through weathering, the cementation may gradually disappear. Take a look at Table 3.3, which examines a number of different types of rock and what the size of grains that make them up are composed of, and looks at both detrital and chemically deposited sedimentary rocks to give you some of the most common names. I'll briefly mention these. I'm reading the right-hand column. Conglomerate and sandstone. Quartzose sandstone only tells you that it was mostly quartz. An arcosic sandstone, which means that it's over 20% feldspar, so arcosic sandstone would have a very pink look to it, characteristic of feldspar. Gray wacky, siltstone, and shales are other examples of detrital sedimentary rocks. Chemically deposited sedimentary rocks include limestone, which is one of the basic building blocks of cement, chalk, chert, gypsum, rock salt, and diatomite. We talked before about how sedimentary rocks we would expect to have been deposited in a horizontal orientation, but they can get tilted by subsequent tectonic processes, or that, and here you see some example of this type of tilting. They're not so horizontal now, but they probably were deposited in the horizontal position when they were first laid down. The next rock type that we're going to look at is metamorphic rocks. These are rocks that are altered or changed by heat, pressure, and or chemically active fluids. And we have two types of metamorphic rocks, foliated and non-foliated. I'll explain what these are in a moment. Foliated metamorphic rocks occur when mineral grains are aligned in a roughly parallel orientation, or banding develops, and this realignment of the grains, or the banding, develops as a result of prolonged pressure that the rock is subjected to. If you take any rock and squeeze it under extremely high pressures for a number of decades, you're going to cause the grains to become altered, and they will realign in a foliated rock. And some examples of this type of metamorphic rock would include slate, which you're probably familiar with from pool tables or an old style roof. Schist is also within this category of foliated metamorphic rocks. And lastly, if the metamorphism goes on for a very long time, you can begin to have the banding develop in a very strong way, and even get to the point where it's melting the rock to form bands that flow through the rock. And that would be a gneiss. So looking at metamorphism of shales, if you take a shale and don't subject it to any metamorphism, you'll find that it's composed mostly of clays, and we would know it as a shale. It would be in the original layers in which it was deposited. But if you have low-grade metamorphism to that type of material, you're going to have very fine clay particles that begin to be transformed into a foliated configuration, so that they become platy minerals. If you increase the metamorphism to get to the point where you have intermediate grade metamorphism, then you might begin to have those platy minerals develop and become more predominant, to the point that microcrystals become large and the rock develops strong foliation, and you'll have a tendency for the rock to break apart along those foliation planes or foliation surfaces. And if you have high-grade metamorphism, such as shown in this gneiss, you'll have the bands of different mineral composing the rock flowing together, as shown here in this gneiss. So of all these, the low-grade metamorphism is the more common, and slate is actually a building material that we've used for a number of years, including the top of this pub in England. The roof of this pub, I should have said. We also have non-foliated metamorphic rocks. If we have high temperatures instead of high pressures, then we're going to get metamorphic rocks of this form. Here we don't have an alignment of mineral grains, and some common examples here would be marble and quartzite. Quartzite turns out to be one of the strongest, stiffest, hardest rocks that we have, and it's rock that's made largely of quartz that is melted down like sandstone, and it's melted down, fused together to form this non-foliated metamorphic rock, probably a quartzite. Marbles would form as a result of metamorphism of limestone. So marble has the same chemical composition as limestone, calcium carbonate, but it results from the metamorphism of limestone. Notice that I mentioned that marble has the same chemical composition of limestone, and if you'll remember, limestone can dissolve when exposed to acids. That's why when you think about a marble countertop in your kitchen or bath, remember that real marble can be easily attacked by acidic materials, so you wouldn't want to leave lemon juice on top of your countertop if it's made of marble. So when we talk about marble countertops in the home, we're probably not talking about actual marble, but sometimes it is real marble that people use for that purpose, but it's going to be prone to weathering. Rocks in the environment, we can recognize that they might be good foundation material in some cases. Slate is good for a foundation material, and it's useful as a building material. We can build outdoor patios of it, and some tiles floors are composed of slate. We can use slate for a roof. Schist is a poor choice for foundation material because it can often contain soft minerals. Gneiss is usually of a very high strength and it's usually perfectly adequate in our foundation. But keep in mind that if you have prominent foliation planes, then those are actually going to constitute layers of weakness. It's what allow slate layers to break off along the slabs that form slate, as you've probably seen it in the past. So that we got to always be watching out for the direction of the foliation planes because those are weaknesses. Here's an example of how we have to watch out for it. These are two configurations for a road cut or a cut through rock in order to put in a road. In one case on the left, you can see the foliation plane dips into the slope that we cut, whereas in the image on the right, the foliation planes allow the potential for a rock slide to occur along the foliation planes. Similarly, if you're going to try and put in a dam in a valley of a river and found out that you have a metamorphic rock, there are some configurations that would be relatively suitable for that application, whereas in others, depending on the orientation of the foliation, we might find that it becomes unsuitable. Why is the one on the right unsuitable? Because the foliation planes in this case, in case B in this image, would allow the passage of water to bypass the dam. So this dam may not be very watertight. You may need to seal up those planes. We look through the experience of engineering experience in the United States. We can see a very infamous example of a dam built on a metamorphic rock in southern Los Angeles. And if you ever watch the movie Chinatown, they don't talk about this application. They hide the truth and make up a different project. But back in the 20s, is part of a process to get adequate water supply for Los Angeles. The St. Francis Dam was built. The only problem was that it wasn't built by an engineer, and it was built right on some metamorphic rock that was a poor choice for the foundation of this material. In cross-section, I'll show it on the next page. In cross-section, what happened is that we had foliation planes, and we had a change from sedimentary rocks in one abutment to metamorphic rocks, and that difference in rock property was enough that it allowed the possibility for cracks to form, and then water could bypass the dam, and that led to the destruction of the dam. And that dam destruction is shown here. In fact, you don't see much of the dam. You see a little piece of it still standing today that didn't break down, but large portions of it did break down and disappear. I have an example of a number of different kinds of rocks that are in layers or strata in a rock. And you'll see that they're not uniform beds, that they've been altered after they were formed. And to describe that kind of process, we need to discuss rock structure. There are a number of different rock structural features. The first of these is fractures. Depending on whether it's weathering or cooling or stress relief, you can get fractures or joints in the rock develop as a result of the change in conditions of those materials. Rocks are really prone to fracturing. Another type of rock structure is folds. If you apply enough pressure, you can get some rock strata to actually bend, and you can see in a number of layers stacked one on top of each other, they actually are become bent together and fold, and we call that folded. Last type of rock structure that we're going to consider are unconformities, which are breaks in the rock deposit or rock orientation, and we'll talk about that in a minute. Fractures can be classified as either joints or faults. If you have no displacement along the fracture, you simply broke into two pieces along a plane or surface, then that's a joint. If you experience displacement along the fracture, if one part of the rock slides across the other side of the fracture, that is a fault. Some of the problems associated with fractures are that the rock might have been very resistant to the passage of fluid, but with the introduction of fractures, they can constitute conduits for fluid passage. In addition, if you have high density of fractures, lots of fractures in a particular part of the rock, you could have zones of weaknesses at those locations where fractures are more abundant. And another problem with fractures is they are subject to weathering, which can widen and weaken the rock along the surface that they leave behind. An example of a fault, and a fault is shown here where we've had a plane across which the part of the rock has slid against the other, and that relative displacement shown by this direction here, that this portion slid across the lower portion of the rock mass. So we have the relative orientation of that displacement shown with this symbol. So faulting is when you have actual displacement across a plane, so it's no longer a joint because we had movement. Next, we'll consider some folds. Folds occur when layers are shortened or compressed, are shortened by lateral compression. So if you deposit some sediments that are subject to deformation by compression, then that would squeeze together to form a folded set of strata such as you see here. And we often need to distinguish anticline from syncline. You're going to find out when we come to oil and gas, for example. You'll need to know the difference between an anticline and a syncline, and those are shown in this image. That we want to consider are unconformities. These represent a significant break or gap in the geologic record. They're important for our understanding of the geologic history that led to the deposition of those formations. And unconformities are often found at the boundary between contrasting rock types. We actually have three different types of unconformities: nonconformities, angular unconformities, and disconformities. And I'm going to show some examples of some angular unconformities, and you can read more about in your text the differences between nonconformities, angular unconformities, and disconformities. On the bottom right, you'll see a picture of an angular unconformity. What happened here is we had a number of horizontal layers that were laid down. Well, these layers were laid down, and in original configuration they were horizontal, but then they were tilted up. Then there was some erosion that occurred, and then there was the deposition of additional sedimentary layers. This interface right here between the angular strata and the horizontal strata would be an angular unconformity. Here's a couple more pictures of angular unconformities. In the upper left, we see layers that probably were originally deposited horizontally, but which were folded, and then there was erosion, and then the deposition of an additional sedimentary beds, and now we have angular unconformity in the upper left image. The bottom right might be a picture that you've seen before. It might be a location that you visited on a vacation to the Grand Canyon. And here in the bottom, about the middle of this image, you can see an angular unconformity. This is actually called the Great Unconformity in the Grand Canyon, and it is one of the more famous geologic structures in the Grand Canyon. That's the end of this module's lecture.